Okay, well, we'll go ahead and get started. So we're starting the last module today. I can't talk super loud because I feel like microwave dog shit, so I'm not gonna talk too loud. I have another class to teach and I need to conserve my energy without passing out in front of you. So we've learned about taking hydrocarbons and doing CH substitution for halogens. And once we get the halogen in the molecule, we can then substitute it. And so now we're going to learn elimination, and that's when the molecule with a leaving group is treated with a base. So an elimination produces a compound with a pi bond, and Module 5 is specifically directed towards alkenes and alkynes. So the first couple lectures will focus on how do we make them using elimination. So that's E2 and E1. And then once we get through making them, we're going to learn addition reactions where we take reagents to add elements to each sp2 hybridized carbon of the alkene. So as we wrap up this semester here, we're going to learn quite a few reactions, so a lot of different conditions that you'll want to keep in mind as you start preparing for the final exam. So the main thing here to highlight, elimination. So that's always going to form a pi bond. And again, this module is carbon-carbon pi bonds. When we get into organic 2, those pi bonds can include carbon-oxygen, so carbonyls, but now we're just focused on alkenes and alkynes. And the ambiguity with this module is the base. So we've learned about other nucleophiles. That's where you're forming a bond to carbon. But now we have to differentiate, is the nucleophile going to act as a base? Which means, is it going to abstract a hydrogen? So the E2 and E1 mechanisms overlap with SN2 and SN1. So it's important to know the reactivity of the reagents, the solvents, and what is going to predominate in terms of substitution versus elimination. So the difference here, again, for the definitions, nucleophilicity is the rate of attack on an electrophilic carbon. So that's a carbon bearing a leaving group. And basicity is abstraction of a hydrogen. So nucleophilicity is typically going to lead to substitution, and then the basicity is going to lead to elimination. The numbers 2 and 1 refer to the kinetics, whether it's bimolecular or unimolecular. So just like with the unimolecular things for substitution, the E1 mechanism forms a carbocation, and then those can undergo rearrangement because they're longer-lived intermediates. So here is the general scenario in the center here. We're going to use this nomenclature alpha and beta just to get our kind of bearings on a carbon chain. So the alpha carbon is bearing an X group that's a good leaving group. So the module we just finished, we had a nucleophile that would displace it and then substitute that X for the nucleophile. So now we're going to learn eliminations, which is abstraction of a hydrogen at the beta carbon. And so you'll notice the mechanism here has one more arrow. So we do an acid-base reaction. This center arrow is the elimination. So these electrons form a pi bond, and then the leaving group leaves. So in bimolecular elimination, we get an alkene, and then this conjugate acid of whatever base we started with. What is kind of weird about this? That's an sp3 hybridized carbon. And so we learned that the pKa of an sp3 hybridized carbon with an H is about 50. So it's a really weak acid. But the fact that we have a leaving group at the alpha position influences the acidity of that. So we do not necessarily have to use a really strong base. And that's what leads to kind of the ambiguity here. And how do you determine whether the base is going to abstract or the base can be a nucleophile? And all of the stuff in the reaction conditions will give you a clue to that. But I would say, to cover our butts here, you're not necessarily going to end up with one product and one product only. You typically end up with a mixture of substitution and elimination. So with this elimination, there's 4 atoms involved in the mechanism. So we have the hydrogen here, the beta carbon, the alpha carbon that it's bonded to, and then the leaving group. So those 4 things have to be in a certain orientation. And so this is going to get back to dihedral angles and Newman projections that we learned in Module 3. So once we identify the carbon bearing the leaving group, that alpha carbon, we have to determine the total number of beta hydrogens. So from alpha, you move out how many beta carbons are there. Then on each of those, you classify them, methyl, methylene, methine. And so you'll get some sort of ratio. And then the question is, which hydrogen will be deprotonated? Because once you do that abstraction, it's going to put the double bond in different places. So there's that thing to worry about. And as we get deeper into looking at the starting materials, the orientation of those 4 atoms will matter. So once you determine the beta hydrogens, they have to achieve a certain dihedral angle, and then from that they can do the elimination. So this dihedral angle must be 180 degrees. So it's specific for those 4 atoms. And we can use some of the reasoning that we learned with substitution, why that is. We said in substitution, the nucleophile has to attack 180 degrees from the leaving group because that's where the anti-bonding orbital is. So the orbital that's not filled. So when we look at a Newman projection, the electron density in this CH bond will then be aligned with that anti-bonding orbital. And so that's why these have to be 180. So that will get into looking at Newman projections, conformational analysis. And then the other thing that will matter for this is the size of the base that we're using. So we can have small bases or large bases, and then we have to match it to the class of beta hydrogen? How accessible are they? So on your sheets there, what you can do, I'll give about 20 to 30 seconds per question. Please fill in your ID with the bubbles. Make sure that you fill that in right so when I scan it, I don't have to do extra work. So if you take butane in the presence of which halogen, it's going to give a product that has the mass spec data as shown. So which halogen was used? So what do you think the answer is? So this is going to be bromine because we have M and M+2, where the ratios are essentially 1 to 1. So when butane is subjected to bromine, what is the major product? So again, this is an example of a radical CH substitution. So you have two unique sets, primary and secondary, and then bromine is selective for what? So bromine is more selective for the secondary, so our response should be C, 2-bromobutane. And so we're going to call that the alpha carbon. What? They're up there. So with 2-bromobutane and the carbon bearing, the bromine is the alpha, how many beta carbons are in the molecule? So how many beta carbons? So we're going to get 2. And we probably want to differentiate them, so beta and beta prime. And how many total beta hydrogens are there? So how many total are there? So there's going to be 5. We have 3 and then 2. So it's important to know how to do that, because ultimately when we look at the different bases, those bases will have a size, and we want to think about the size of the base and how it can be able to access any of those type of hydrogens. So before we get too far into the arrow pushing here, because there's 2 different types of beta hydrogens, we're always going to form a double bond between an alpha and a beta carbon. We have 2 types of beta hydrogens. That means we can form different products. And so the distribution of those products is going to be related to the stability of the double bond that's formed. So in reviewing the orbitals for an alkene, we have that central sigma bond there. And then the double bond results from the overlap of the p orbitals. That's the pi bond. Each carbon is sp2 hybridized. It contributes 1 electron, so we form the pi bond. A total double bond is worth 611 kilojoules per mole. A sigma bond is worth 347, and so therefore the pi bond is worth 264. So it's not as strong as a sigma bond, but overall it contributes to the double bond being pretty strong. And so what happens, because the orbital overlap of the p orbitals has a cloud on top and bottom, it locks in the geometry about that alkene. So when we look at the alkene down here, and then look at the numbering of the substituents, 1, 2, 3, 4. The 1 and the 2 are staying the same here, but on this one, 3 and 4 are flipping. It takes some energy to break that 264 so that these things can form the other isomer. So the relationship between these 2 structures are called geometrical isomers. And then that will get into this Z and E nomenclature we use to differentiate them. So when we're evaluating the question, which beta hydrogen is going to get abstracted, we want to do an abstraction that's going to form the most stable alkene. And alkenes are ranked according to the number of carbon substituents bonded to each sp2 hybridized carbon. So the ranking is, you identify the alkene, so that's the 2 sp2 hybridized carbons. Then on each one, you're counting the number of carbon substituents. If it's hydrogen, you don't count it. So tetrasubstituted alkenes are the most stable, followed by trisubstituted, and then there's 3 different flavors of disubstitution: trans, geminal, and cis. Geminal means same. That's where the substituents are on the same carbon. And then monosubstituted. So when you evaluate which beta hydrogen is going to get abstracted, you predict the percent major versus minor based on this trend here. So to put it another way, you really have to draw all the possible products, then identify them according to this, and then you can rank them. But again, the The star, asterisk, the caveat to that is the nature of what base you're using, because certain bases will flip the order and how you predict the rank. So that stability trend is measured experimentally through this reaction, so hydrogenation. And this is an example of an addition reaction. So elimination forms a pi bond, an addition reaction adds things back to a pi bond. It's called addition because we have hydrogen gas, so H2. In our alkene, each carbon is going to get an H atom. So H2 has added across the double bond. And in the chart here, we have a series of those alkenes that tell you what class they are. So monosubstituted, this just has one carbon substituent. We have di, which is cis, that means the substituents are on the same side. Geminal, they're on the same carbon. Trans, they're on opposite sides. Tri-substituted, 1, 2, 3, and then tetra. Each carbon has 2 carbon substituents, so a total of 4. So when you take those alkenes, you add hydrogen to hydrogenate it, then you measure the heat that's given off. So this is what's measured. We see this stability trend. The mono is giving off negative 126 kilojoules per mole. And the tetra is giving off negative 111. And so in terms of stability, to understand the meaning of negative numbers, if you start at 0 and you think about just going down to a negative number, whatever you hit first is the most stable. So negative 111, you hit that before you hit negative 126. That evolves more heat, meaning it's less stable. And then you can see the trend in between them. So the ranking of the number of substituents helps you figure out what is going to be the preferred product. And really, you want the double bond to have as many carbon substituents as it can. Any questions? So our next question here, which of the following is the most stable alkene? So what do you think? I heard C. I could see why you might think that, but it's not the right one, so it's D. So notice there's not a number given before the alkene, so that's when you assume it starts at position 1. So in terms of the classes, this is mono, this is di-cis, this is di-geminal, and this is di-trans. So D would be the correct answer here. So the next couple of questions, let me just give you a preview with the model here. So we took butane, that's the 4 carbons. We did a CH substitution for bromine, so that puts it at methylene group, so it's 2 bromobutenes. And now we have the 2 beta carbons, which I'm holding in my hand. This is a methyl group, and then this is a methylene group. This carbon over here at the end is not going to matter because from the alpha carbon, we go to a beta carbon, and then from there we have to pick a hydrogen. So we can't go out over here because that's the gamma position is too far away. So we're looking at, for this next run of questions, that the beta carbons bearing the beta hydrogen. So if this is your base, the base is going to come along and see some things, abstract a hydrogen, and really to understand it, the best thing to do is abstract hydrogens from each beta carbon, draw all the possible products, and then rank them. So it says which beta hydrogen will be abstracted to form the least stable alkene. So what do you think it is? So it's going to be A. So we haven't pushed the arrows yet, but I've said you're always forming a double bond between an alpha and a beta carbon. So without pushing the arrows, we know that we have to draw the double bond there. And so that is going to be the alkene when we do that elimination. And so that's mono-substituted. So which beta hydrogen will be abstracted to form the most stable alkene? So what do you think? So C. So this is the one we'll get into because there's a little bit more nuance here. HA has 3 hydrogens, or this beta carbon has 3 of the same hydrogens in a methyl group. This beta prime has 2, it's a methylene. But what can happen is those hydrogens are actually different, even though they're bonded to this same beta prime. So we form the double bond now starting at the 2 position, but depending on which hydrogen we abstract, we can lead to different geometries. So now I've put the stereochemistry in here, and it says which one of these will be abstracted to form the trans alkene. So the nuance is that the hydrogen on the beta carbon has to be 180 degrees to the leaving group X. So which one do you think it is? So it's going to be C. And so in the model here, we have the bromine coming out towards you. We have this alpha hydrogen going back. And then B is out towards you, and then this one back here is C. So why is it C? It's 180 degrees from the leaving group. And the other thing, when you look at in the chain that's drawn on the board, these 2 carbons, they are opposite one another. And so that means this is getting abstracted and that's leaving. So these groups are going to end up on opposite bases. Or put it another way, if we look at the Newman projection. So this is HC in my left hand and the bromine in my right. Look at the orientation of the methyl groups. So here and here, they end up 180. So that means you will get the trans product from that. So even though this carbon has 2 hydrogens, to get to the trans geometry, it has to be this one. And so you can see where we're going with this. To abstract this one for the mechanism, you have to do a rotation. So now that hydrogen in the leaving group are anti as best I can hold it. Then look at the orientation of the methyl groups. So see how it changes. So that's going to give you a different geometry. So the nuance of this is the hydrogens of that CH2 are actually different because they're going to go to different products. So which one will give the cis alkene? And to recap that, you have to rotate about that sigma bond to put the correct hydrogen 180 degrees from the bromine. And then what happens is the terminal methyl groups, their orientation to one another will change. And so this one was which hydrogen? This ends up being B. So that's essentially what will happen is now this HB is anti to the bromine, and so the methyl groups of that chain are on the same side now, or eclipsed. So in this one, we can think of them as being anti. So the best thing to do with these problems to understand how they proceed is to get your model kits, make the models so that you can do the bond rotations, see how these other groups then, what their orientation relative to each other are to predict whether that hydrogen is going to give you cis or trans. So the mechanism, just again, the structured around on the slide. So now this is here. This. So the thing here is this H, beta carbon, alpha carbon, bromine, those now lie in a plane. And so the two carbons in that plane are going to form the double bond. So the reason they have to be, if we look at the Newman projection, they have to be that 180-degree dihedral. We have a carbon-bromine sigma bond. The anti-bonding orbital is right behind it. So what we saw with substitution, it has to attack there. Now with elimination, the electrons to fill that anti-bonding orbital are coming from this sigma bond. So it has to directly align with that empty sigma star orbital. So that's called an anti-elimination, or as your book says, a lot of other terms, beta elimination, dehydrohalogenation, all these different terms. But we need those central four atoms in a plane. And then from that, you sprout off the different substituents. So the electrons move this way. Here we have the base is supplying electrons. In this case, we're using sodium ethoxide. So it's going to abstract a beta hydrogen. The electrons in this bond form the new double bond, and then the leaving group leaves with these electrons. The transition state organizes itself like this. We're partially forming this bond between oxygen and hydrogen. We're partially breaking that bond, partially forming a pi bond, and then partially breaking the leaving group bond. And the result is our alkene, the conjugate acid of our base, and then this sodium bromide is the inorganic product. So the key thing here is from your models, identifying the alpha position, the beta position, making a Newman projection, then to see what hydrogen aligns best. So that, again, that alignment is due to the fact that the sigma star is empty, and so the electrons have to go somewhere. In the beta hydrogen that is aligned with it through that 180-degree dihedral will allow that to happen. So in the example that we used with this 2-bromobutane, you have that methylene group, which has 2 hydrogens, but depending on which one you deprotonate, you end up with the trans or the cis. So what will influence the product distribution in terms of major versus minor is that conformational analysis we learned with the Newman projections. So in general, trans products will be favored because that minimizes the strain observed in the transition state. So the reaction coordinates get a little bit more complicated now because we have this starting material, and because of the rotations that can happen, there can be the most stable conformer and then this other thing, the reactive conformer. And those can have different energies and they can lead to different products. So the thing that's the most stable in terms of a Newman projection might not be the reactive conformation. And again, that's where the heat and other solvent and things come into play. So see what we're looking at here. The carbon in front here, that's carbon 3. So we're looking from carbon 3 to 2 in this Newman projection, and then we see the 2 different hydrogens. So of the bond rotations of that front carbon, so I'll put some numbers in here. So those refer to the carbon chain. This one where it says carbons 1 and 4, methyl and methyl are anti. That's the most stable Newman projection because we're minimizing steric interactions. And from that, it's going to be this hydrogen that gets deprotonated, which will lead to the trans product. But because there is sigma bond rotation, you can have this other one. That puts carbon 1 and 4 in this 60-degree or gauche, so that's less stable. But it can still form. Now this other hydrogen, which is different, will lead to the cis geometry. So in terms of major versus minor, this would be the major product. And that would be the minor product. So there's 2 things to rationalize here. Not only the stability of the alkene product, but the conformers that lead to it. They just so happen to align in this case. That this ground state conformation is the reactive one that leads to the most stable product. But again, that's not always the case, and you have to evaluate each reaction independently. So here's our reaction coordinate, and what we want to think about that's different is time is sort of moving in both directions because it leads to different products. So there's one of the ground state conformers, that's the most stable one. Here's a bond rotation to the other. And then kind of from this center point, either moving right or left, they're going to form the different products. So we would expect this one to be more populated. And then it's going to go through a transition state and lead to the trans product. if there's enough energy, we can get to this one. It has its own transition state, and it's going to lead to the other product. So we can evaluate from the ground or reactive state, and then also the products themselves. Any questions?
So we assume the more stable one is like the starting thing, and to get to assist, it has to rotate.
Yeah. So the cis, again, what you would predict it, without seeing any data, you would predict this would be minor, because just in the starting material itself, this conformation is more populated. So to get to here, you have to put energy in to begin with. Then you have to put even more energy to get over its transition state. So this one, that little ball has to go up like a longer path, whereas here it's just getting over that to go to the product. So that's the general theme for acyclic cases. So we'll finish up here today on these cyclic ones. So the same principles apply, that you're going to identify an alpha carbon, identify the beta carbons, but now we're going to limit it to really just a 6-membered ring. Those are the most informative. So we have a carbon bearing a leaving group, O-tosyl. So that's a sulfonate ester. That's our leaving group. We're going to call that the alpha carbon. And then we're going to run through this analysis and see how it can get a little bit more amorphous in terms of which of these beta hydrogens achieves the correct reactive conformation. So in this compound, next question, how many beta carbons are there? So I was given the sign, there's 2. So we have 2, and they are different. One's a methylene and one's a methyne. So if we want to convert that flat cyclohexane into a chair, which chair is the best representation of that? So of the 2 substituents, they're in a 1-2 relationship. The tosyl group is shown as down or away from you, and the methyl is up or towards you. So what do you think? D is the correct choice. So B is wrong because that's showing a 1, 3. A is wrong because that's down and down. C is wrong because that's up and up. So D is correct because it's 1, 2, and then it's down and up. So for each chair conformation, remember there's a chair and a chair flip. So of these two, A and B, in the ground state, which is the more stable one? Some pretty enthusiastic A's to begin with. And so why is that? So we have more equatorial substituents. So conformer B has these axial ones, and the axial substituents are what leads to these interactions with the hydrogens that are 3 atoms away. And so we have now 2 conformers, but really based on the restraints for elimination, only one of them is reactive. So between A and B, which one's the reactive conformation? So you want to keep in mind that HCCX has to be 180 degrees. So between A and B, which one's the reactive conformer? So B is the reactive conformer. So again, to reiterate that, in the energy well, A is going to be more stable because the things are equatorial, but B is going to be the one that reacts. So A has to get to B, and then it can go to an elimination. The conformer A does not meet the requirements for an elimination. So which one of these hydrogens has the correct dihedral angle to the tosyl group for an elimination? So C. So what you're looking at is the reactive conformer of the 2 ground state conformers. This is the less stable one because the substituents are now axial. For an elimination in a ring, the leaving group must be axial, because that's the only way you're going to get this 180-degree dihedral angle. So of the beta hydrogens, so there's alpha, beta prime, and beta. HA will never eliminate. HD will never eliminate. If you draw the other chair conformer, you put in those hydrogens, the tosyl group is equatorial, so it doesn't matter if a hydrogen's axial or not, it still can't eliminate. So what I highlighted in green is that relationship of those 4 atoms. If you looked at a Newman projection down that bond, you would see that the H in the leaving group are 180. And then using that knowledge, you're just plunking the double bond right there. So once you do that, what is the product going to be? So I'll give you a hint. We have to get rid of the leaving group, so it can't be them. The choices you're left with are which beta carbon the H is coming from. So A is the correct response. And so another sort of explanation to this, why you can't always just use the alkene stability ranking. So C is a tri-substituted alkene, and A is di-substituted. If you were just using the stability of alkenes, you would say, well, it's got to be C because that's more substituted. But as we see from the reactive conformation, A is going to be the major product because we achieve the right dihedral angle. So there's always these, in the engineering workflow of yes or no, these questions. You have to ask all these questions for each reaction you're evaluating. So any questions with the cyclic eliminations? So with that, in the last 15 minutes here, we're going to look at the bases. And now the thing with the bases, there are 2 named reactions that flow with the size of the base. How does the size of the base influence which beta hydrogen can get abstracted? And so that will partition the major and minor alkenes differently. So even though these type of hydrogens are weak acids, the fact that we have this arrangement where the leaving group kind of increases the acidity of that, we can use fairly weak bases to do these deprotonations. And so here are some oxygen bases. Sodium hydroxide, sodium methoxide, sodium ethoxide, and then tert butoxide. And then these are kind of the sizes of those. Ethoxide is maybe the weird one because it's in between, but we go from small to large. So tert butoxide is this. The metal that's used can really be, lithium, sodium, or potassium, and then to a finer extent, if you went on to study this as your life career, you can add other things in there that sequester those things away, changing the reactivity. But for now, it really doesn't matter what that metal is for our purposes. And just think of tert butoxide is being pretty big because we have this bulky group here, and then the other ones are kind of small. Once you do the deprotonation, you get the conjugate acid, and then those are the pKa values. So you can see that these are pretty weak bases to begin with. So those are the oxygen ones. Of these forms, notice these are all ionic. You have a metal and then some anion. And the practical issue of using those is the solubility in the reaction. So I might just say the nitrogen bases, notice these are all neutral. So they're readily soluble in organic solvents. And these have some structures you probably haven't seen before. And my little asterisk here is the sodium amide. That one's ionic as well. But the other ones are neutral. So when these four other ones do a deprotonation, you're forming a conjugate acid that's positively charged. And so those are ammonium salts, and then their pKa's are much lower than. So we've moved from about 16 to 10. The other thing I want to point out about these, if you look at the nitrogens, these are all tertiary amines. So that means they're nitrogen atoms with 3 carbon substituents, and then furthermore, based on what those are, they're pretty bulky. So nitrogen has a lone pair. When it's acting as a base, that lone pair is abstracting a hydrogen. But the ambiguity again with this, especially when you're studying for the final, is when you see something like this, how do you know it's acting as a base and not a nucleophile? So again, the solvent and all the other conditions you see will help you figure out, is it substitution or elimination? Generally, these are bases and not nucleophiles. Because of these really bulky groups, we know that from the SN2, we have to have a certain trajectory, and the lone pair has to be available to form that bond. So these are really bad nucleophiles. They're better bases. And so why does this matter? Why does size matter? So the bulkiness of that base needs to be matched with the type of beta hydrogen you're abstracting. And so that's classified in 2 ways, Zaitsev and Hoffman. A Zaitsev elimination uses a small base, meaning that it's going to go for the more hindered beta hydrogens. That's typically the beta carbon with the least number of hydrogens. The outcome of that is the more substituted alkene. A Hoffman elimination would use a large base like potassium tert butoxide. Because that is a large base, it has to go where the hydrogens are most accessible. And that's typically a beta carbon with the most hydrogens. And therefore, you get the least substituted alkene. Any questions? So we'll put this into practice with the last couple questions here for your sheets. So we have 2-bromo, 2-methylbutane. And this question is related to the unique types of hydrogen sets. So how many total unique hydrogen sets are there?
3.
So this one has 3. So we have these 6, those 3, and those 2. And again, what's useful about this, I think, is of that, then you can say, okay, which of these are actually beta hydrogens? Those are the reactive ones. Then you can evaluate kind of their number. Are they accessible or not accessible? And then flow into the Zaitsev versus Hoffman. So of those sets, how many are beta hydrogens? So of these 3 sets, only 2 of them are going to be classified as beta. So this would be beta, and then these 2 would be the beta prime. So these 6 are going to take this beta designation, and then the beta prime are those 2. So we get 6 to 2. So our starting material we're going to treat with potassium tert butoxide. That's a big bulky base. So which grouping of beta hydrogens is the most accessible to that? So those 2 betas were the same, beta prime was different. So the beta ones, since they're CH3 groups, those are methyl. Beta prime is CH2, it's methylene. You have this big bulky base, so when it's floating around in solution and it sees this, it's going to access the beta ones more readily because they're less hindered. So for this one, we're going to get methyl. So when it does a deprotonation at one of those methyl groups, what is the classification of the alkene? Anyone want to hazard a guess? I heard a mono, that's not correct. So that's di-substituted. So again, of the two sp2 hybridized carbons, you're counting the carbon substituents. So you have 1 and 2. 1 and 2. So of that product, what's a further classification of it? The word means twins. Any guesses? So it's geminal. Together, 1, 2. So geminal, cis, and trans are the three alkene kind of designations. Vicinal is more for when you just have a carbon chain that's acyclic and no alkene. Vicinal means 1, 2, but we're not dealing with cis or trans or geminal at that point. So what is the name of that product? Any guesses? So 2-methyl-1-butene. So again, this is a Hoffman elimination because we formed the least substituted alkene. And so what is the name of the minor product that would be formed? That's when we would eliminate from the beta prime. Any guesses? So A, 2-methyl-2-butene.